Have you ever stopped to think that the empty space between the stars, that absolute black that we see when we look at the night sky, is actually not really empty? That even when you remove all matter, all radiation, all air, every atom, every subatomic particle, even when you create the most perfect void possible, something extraordinary is still happening there? Neil deGrasse Tyson, one of the most influential astrophysicists of our time, has shared a revelation that defies everything our intuition tells us about reality. The void is not empty, and even more disturbing, it is in constant motion, vibrating, pulsing, creating and destroying particles in unimaginable fractions of a second. And this movement of nothingness could be the key to understanding why the universe exists. Why you exist right now reading these words. What happens when you remove absolutely everything from space? The answer will completely change your perception of the fundamental nature of reality. For centuries, philosophers and scientists believed that the void was exactly that, the complete absence of anything. A neutral state where nothing happens, where time and space exist but nothing disturbs them. Aristotle went so far as to state that nature hated a vacuum, that the universe simply would not allow the existence of a truly empty space. But what quantum physics revealed in the 20th century is so bizarre, so counterintuitive, that even today many physicists are uncomfortable trying to explain the implications. If you are one of those who love it when science turns our certainties upside down, who are fascinated when we discover that reality is much stranger than we imagined, then subscribe to the channel now, because what we are going to explore today will blow your mind in ways you can't even imagine. And we have many more scientific revelations waiting for you. Let's start with a disturbing thought experiment. Imagine that you have the power to remove absolutely everything from a given volume of space, say a cube measuring 1 meter on each side. You remove the air, obviously, every molecule of oxygen and nitrogen. But it doesn't stop there. You remove every errant atom, every particle of cosmic dust, every photon of light that is passing through this space. You cool this volume to absolute zero, minus 273.15 degrees Celsius, the lowest possible temperature in the universe, where theoretically all atomic movement ceases. You even remove the gravitational waves that are constantly tearing through the fabric of space-time. What's left? Your intuition probably says, nothing, absolutely nothing. A perfect vacuum where nothing happens, where there is no energy, there is no movement, there is no change. But your intuition is deeply, fundamentally wrong. What remains is not a quiet, inert void. What remains is something physicists call a quantum vacuum. And that vacuum is buzzing with activity, vibrating with an energy that permeates all of space, creating and annihilating pairs of virtual particles on timescales so small they defy our ability to measure, but which leave detectable and measurable effects in reality. Neil deGrasse Tyson explains it in a way that perfectly captures the strangeness. The vacuum is not the lowest energy state possible, not the absolute zero of existence, but rather a seething sea of quantum possibilities that never rests, that never stops moving. To understand how we came to this disturbing understanding of reality, we need to go back in time to the beginning of the 20th century, when quantum physics was being born from the brilliant minds of scientists like Max Planck, Niels Bohr, Werner Heisenberg, and Paul Dirac. These thinkers were facing a fundamental problem. The behavior of subatomic particles simply did not make sense within the laws of classical physics that Newton had established 250 years earlier. Electrons did not behave like little billiard balls orbiting a nucleus, but rather like probability waves that existed in multiple states simultaneously until they were observed. It was in this revolutionary context that Werner Heisenberg formulated in 1927 what we now know as the uncertainty principle. And it is here that our story about the moving void really begins. Heisenberg's uncertainty principle establishes something fundamental about the nature of reality. There are pairs of physical properties that cannot be known simultaneously with arbitrary precision. The most famous example is position and momentum. The more precisely you know where a particle is, the less precisely you can know where it is going and how fast. But there is another pair of uncertain properties that is crucial to our understanding of emptiness: energy and time. What this means is extraordinary and counterintuitive. It means that on extremely small time scales, conservation of energy can be violated. You can literally grab energy out of thin air as long as you give it back quickly enough. It's as if the universe allows you to borrow money from the cosmic bank, as long as you pay it back before anyone notices. And the shorter the period of time, the greater the amount of energy that can be borrowed. This is not philosophy or metaphysical speculation. This is rigorous mathematics, equations that have been tested and confirmed in thousands of different experiments. In 1948, a Dutch physicist named Hendrik Casimir was working at Philips when he made a surprising prediction based on this idea of quantum fluctuations in a vacuum. He proposed that if you placed two perfectly parallel metal plates very close to each other in a vacuum, they should be pushed against each other by a tiny but measurable force. The reason is fascinating. Between the plates, only electromagnetic waves of certain wavelengths can exist, those that fit perfectly into the available space. But outside the plates, in the surrounding vacuum, waves of any length can exist. This creates a differential pressure. As flutuações quânticas do vácuo literalmente empurram as placas uma contra a outra. When this effect was finally measured accurately in the 1990s, the results agreed with theoretical predictions with impressive precision. The empty void had just exerted a measurable force on macroscopic objects. The void was moving. It was doing something. It was interacting with real matter. But what exactly is moving in this void? To answer that, we need to delve deeper into the bizarre nature of quantum reality. And here is where Neil deGrasse Tyson often emphasizes a crucial point. The quantum vacuum is not empty space filled with some kind of substance, but rather the very fabric of reality in its most fundamental state. And that fabric is constantly writhing, vibrating, creating pairs of particles and antiparticles that arise from energy borrowed from the void and annihilate each other again in fractions of a second so small we can barely conceive. These are called virtual particles, and although they exist for periods of time so short that they violate the conservation of energy in a way permitted by the uncertainty principle, they are absolutely real in their effects. Imagine the void as the surface of an ocean seen from very far away. From a distance, it appears smooth and calm. But if you get closer, you will see that it is constantly agitated by small waves, foam, bouncing, and falling drops. The quantum vacuum is like that, but in dimensions of space and time so tiny that you would need to look at scales smaller than a millionth of a millionth of a millionth of a centimeter, and at time intervals smaller than a millionth of a millionth of a millionth of a second. On these unimaginably small scales, pairs of particles are constantly flickering into existence. An electron and a positron here, a quark and an antiquark there, a photon fading in and out. The energy to create these particles comes from the vacuum itself through this bizarre quantum permission to temporarily violate the conservation of energy. And the particles must annihilate each other and return the energy before the time allowed by the uncertainty principle expires. It's as if reality is a computer screen where pixels are constantly flickering on and off in frantic patterns, but so fast that when you step back, all you see is a steady image. These vacuum fluctuations have profound consequences. They affect the behavior of real particles passing through space. An electron traveling through a vacuum is not actually traveling through empty space, but rather swimming through this seething sea of virtual particles that appear and disappear. And these interactions slightly change the electron's properties in ways that we can measure with extraordinary precision. In fact, some of the most accurate predictions ever made in all of science come from calculations that take these quantum vacuum effects into account. Quantum field theory predicts the electron's anomalous magnetic moment with an accuracy of 1 part in a trillion, and experiments confirm these predictions. This is not abstract philosophy. This is the most accurate description of reality that humanity has ever managed to create. Now the story gets even stranger and more fascinating when we consider not just what happens in small volumes of vacuum here on Earth, but what happens to the vacuum on a cosmic scale, across the entire observable universe that spans 93 billion light-years across. And this is where Neil deGrasse Tyson's revelation about the movement of void connects with one of the most disturbing discoveries in modern cosmology: dark energy. In 1998, 2 independent groups of astronomers were studying type Ia supernovae, extremely bright stellar explosions that serve as standard candles for measuring cosmic distances. What they discovered shocked the scientific community. The universe was not only expanding, as we had known since Edwin Hubble's observations in 1929, but it was expanding faster and faster. Expansion was accelerating. That didn't make sense. Gravity, the only force acting on cosmic scales, should be slowing expansion, pulling everything back, perhaps eventually collapsing the universe in a big crunch. But something was pushing space to expand faster over time, working against gravity, and that something seemed to be evenly distributed throughout empty space. Scientists have called this mysterious entity dark energy, and calculations based on the observations have revealed something astonishing. Approximately 68% of all energy in the universe is in the form of dark energy. Let that sink in for a moment. More than 2/3 of everything that exists in the universe is this mysterious substance that permeates the void and makes it expand. You, me, all the stars, all the planets, all the black holes, all the invisible dark matter that holds the galaxies together, all together represent just 32% of the total energy of the cosmos. The rest is the void that moves, that pushes, that transforms. And here's the fascinating connection. The simplest explanation for dark energy, although not the only one, is that it is precisely quantum vacuum energy, that intrinsic energy of empty space that arises from the quantum fluctuations we discussed. If you calculate the energy density of these quantum fluctuations using quantum field theory naively, you get an absurdly large number, something like 120 orders of magnitude larger than the observed value of dark energy. This is called the cosmological constant problem, and is possibly the biggest discrepancy between theory and observation in all of physics. Something is canceling out almost all of this vacuum energy, leaving only a tiny residue, but enough to dominate the dynamics of the entire universe. No one knows exactly what is doing this cancellation or why the residual value is exactly what it is, but the fact remains, the vacuum has energy, the vacuum is doing something, the vacuum is moving the very fabric of space-time and determining the ultimate fate of the cosmos. Where are you watching this from now? Comment your city or country, because it is incredible to think that it doesn't matter if you are in Brazil, Portugal, the United States, or anywhere else on the planet. The vacuum around you, the space between the atoms of your body, the space between the Earth and the Moon, is participating in this same cosmic dance of accelerated expansion. We are all being carried along with the movement of the void that permeates the entire universe. But wait, because there is yet another layer of strangeness about the moving void, and it has to do with the very origin of the universe in the Big Bang. The theory of cosmic inflation, proposed by Alan Guth in 1980, and refined by many other physicists since then, suggests that in the first moments after the Big Bang, there was a phase in which the universe expanded exponentially fast, repeatedly doubling in size in infinitesimal fractions of a second. In a time interval smaller than a millionth of a millionth of a millionth of a millionth of a second, the universe could have grown by a factor of at least 10 to the 26th power, transforming a region smaller than an atom into something the size of an orange or larger. What caused this inflation? You guessed it. Once again, it is the vacuum, or more specifically, a hypothetical quantum field called the inflaton that filled the early universe and whose vacuum energy state was in an excited state, a false vacuum, which decayed into the true vacuum, releasing colossal energy that drove inflationary expansion. But here's the truly disturbing part that Neil deGrasse Tyson loves to emphasize. The quantum fluctuations during this inflationary phase were stretched to cosmic scales and became the seeds of all the large-scale structure we see in the universe today. The galaxies, the clusters of galaxies, the superclusters, the cosmic voids, the entire cosmic web of structure that spans billions of light-years originated in tiny quantum fluctuations in the vacuum that were amplified by inflation. The movement of the vacuum, these quantum ripples in nothingness, literally created the structure of the universe. You, your family, your planet, your galaxy, everything exists because the void was moving erratically in the first few moments of time. Observations from the Planck satellite that mapped the cosmic microwave background radiation, the afterglow of the Big Bang, confirmed that temperature fluctuations in this radiation follow exactly the pattern predicted by quantum inflation. The vacuum left its signature on the oldest light in the universe. More than that, some physicists, including the legendary Stephen Hawking before his death, have argued that the universe itself may have arisen from a quantum fluctuation in a vacuum. The Hartley-Hawking boundaryless proposal suggests that if you go back to the Big Bang and use the quantum theory of gravitation, although we do not yet have a complete theory, the question, what was there before the Big Bang, may not make sense because time itself emerges from the initial quantum state, and that state can be thought of as a fluctuation of the quantum vacuum of a more fundamental theory. It's like asking what's north of the North Pole. The question takes on a structure that doesn't really exist. The entire universe, with its hundreds of billions of galaxies, each containing hundreds of billions of stars, may essentially be a large-scale quantum event, a fluctuation that has borrowed energy and will eventually have to be returned when the universe returns to a vacuum in some unimaginably distant future. This is speculative, of course, and there are intense debates among theoretical physicists about whether these ideas make sense or whether they are just mathematical games. But the crucial point remains. The vacuum is not passive. It is not an inert stage on which physics happens, but it is an active participant, perhaps the most fundamental participant in reality. Let's delve even deeper into the philosophical and existential implications of this. What does it mean to say that the void is in motion? For centuries, philosophers have made a fundamental distinction between being and non-being, between existence and non-existence. Parmenides in ancient Greece argued that non-being cannot exist because thinking about it already gives it a form of existence. The quantum vacuum completely blurs this distinction. It is not existence in the classical sense of there being permanent particles and energy there, but it is also not non-existence, because there is clearly something going on, there is structure, there are measurable properties, there are effects on reality. Philosopher Martin Heidegger famously asked, "Why is there something rather than nothing?" Quantum physics suggests that this may be the wrong question because nothing is not really nothing, and the transition between something and nothing is not a sharp boundary, but rather a continuous spectrum of quantum states with different levels of reality. Neil deGrasse Tyson often observes that this understanding of the vacuum should humble us about our intuition. We have evolved to deal with boulder-sized objects and animals moving at speeds we can follow with our eyes, in a world where gravity is the dominant force and where quantum mechanics and general relativity are irrelevant. Our intuition was calibrated by millions of years of evolution to survive on the African savanna, not to understand the behavior of subatomic particles or the structure of space-time. This is why quantum reality seems so strange, not because it is objectively strange, but because our brains are not built to understand it intuitively. The math works, the predictions are confirmed with extraordinary accuracy, but our visceral experience of reality fails to capture what is actually happening. The moving vacuum is a perfect example of this. It seems impossible, it seems contradictory, but it is simply how reality works at its most fundamental levels. There are also fascinating practical implications of these ideas. Some physicists have speculated about the possibility of extracting energy from the vacuum, a kind of zero-point energy that could, in principle, be harnessed. Casimir fluctuations have already demonstrated that a vacuum can exert forces, so why not usable energy? The answer is complicated. Although the vacuum contains energy, extracting usable energy from it requires you to create an energy state even lower than the vacuum, and it's not clear whether this is possible or permitted by the laws of thermodynamics. If it were possible, it would literally be getting energy out of thin air, a perpetual motion machine of the most fundamental kind. Most physicists are deeply skeptical, but the debate illustrates how these questions about the nature of the vacuum have the potential to change not only our philosophical understanding of reality, but also our technological capabilities. Now let me share with you something that will really make your mind explode about the motion of the void, something that connects all of these ideas in a way that we are still trying to fully understand: the concept of quantum tunneling through the vacuum and its implications. Implications for the stability of our universe. Remember we mentioned the idea of a false vacuum during inflation? Well, there is a disturbing possibility in modern particle physics. The vacuum we live in now, what we call the ground state of quantum fields, may not be the true lowest energy state. It may be a false vacuum, a metastable state that is locally stable, but not globally energy minimum. It's like a ball sitting in a depression at the top of a hill. It's in local equilibrium and won't roll on its own, but if something pushes it a little, it will roll down the hill to an even lower energy state. The problem is that if our vacuum is metastable, then, through quantum tunneling, which is the phenomenon where particles can cross energy barriers that classically should be insurmountable, a small bubble of true vacuum could spontaneously appear somewhere in the universe. And once this bubble appears, it would grow at the speed of light, converting all the false vacuum on its way to true vacuum. The laws of physics inside this bubble would be different. The masses of fundamental particles would be different, the chemistry would be different, and everything we know, all the complex structures like atoms, molecules, stars, planets, and life, would simply no longer be possible. It would be the end of everything. Not gradual like the thermal end of the universe 200 trillion years from now, but instantaneous and complete, spreading through the cosmos at the speed of light without any prior warning. Based on what we know about the properties of the Higgs boson discovered at the Large Hadron Collider in 2012, some calculations suggest that our vacuum may indeed be in this metastable condition. Uncertainties in measurements mean we don't know for sure. It could be that we are in a truly stable vacuum, but the possibility is there. The vacuum that we think is the lowest state of energy, the floor of reality, may be preparing to fall to an even lower level. And when that happens, it will be the end of everything. Neil deGrasse Tyson described this as one of the most aesthetically interesting ways the universe ends. Without warning, without the possibility of escape, just an instant where everything that exists simply ceases to be possible. That sounds scary, and it is, But before you panic, let me add some comforting context. Calculations suggest that if our vacuum is metastable, the rate of decay is so incredibly slow that the expected lifetime of our false vacuum is much, much longer than the universe's current age of 13.8 billion years. We're talking about timescales of 10 to the 100th power of years or more. So it's not something you need to worry about today, or in a million years, or even in a trillion years. But the conceptual point remains. Even the vacuum, that state that we thought was as stable as possible, the ground of reality, may be in motion in the deepest sense, preparing for a transition that would transform everything. What do you think of these possibilities? Which of these revelations about the vacuum impressed you most? Quantum fluctuations creating and annihilating particles? Dark energy driving accelerated expansion? Vacuum fluctuations creating the structure of the universe during inflation? Or the possibility of vacuum decay? Comment your opinion below. I love knowing what you think about these ideas that challenge our intuition about reality. There is yet another fascinating dimension of vacuum motion that we need to explore, and it has to do with the intersection of quantum mechanics and gravity, specifically the phenomenon of Hawking radiation in black holes. Stephen Hawking showed in 1974 that black holes are not completely black, but actually emit radiation due to quantum effects near the event horizon. The mechanism is elegant and disruptive. Pairs of virtual particles are constantly emerging from vacuum fluctuations throughout space, as we've discussed. Typically, these pairs appear and annihilate each other so quickly that they do not violate energy conservation beyond what is allowed by the uncertainty principle. But near a black hole's event horizon, something special can happen. If a particle-antiparticle pair appears exactly at the event horizon, one of the particles may fall into the black hole, while the other escapes to infinity. From the perspective of a distant observer, it appears that the black hole has emitted a particle. But where did the energy come from to create this real escaped particle? It came from the mass of the black hole. The black hole loses mass, slowly evaporates, through a process that is fundamentally driven by fluctuations in the quantum vacuum. The vacuum around a black hole is moving, creating pairs of particles, and this literal motion translates into real radiation that we can, in principle, detect. Although for stellar mass black holes, the radiation is so weak that it is completely dominated by the cosmic microwave background. But for microscopic black holes, if they existed, the Hawking radiation would be intense. This raises profound questions about the nature of information and quantum mechanics. If a black hole completely evaporates through Hawking radiation, what happens to all the information about the particles that fell into it? Quantum mechanics says that information must be preserved, but it appears that it is destroyed when the black hole evaporates into random thermal radiation. This is the black hole information paradox, and its resolution likely requires a deep understanding of how gravity and quantum mechanics unify, something we don't yet fully have. But the point for our discussion is clear. The vacuum around a black hole is not passive. It is actively participating in the evaporation process through its quantum fluctuations, and these fluctuations have real consequences for the fate of massive objects in the universe. Think about this for a moment. The densest object we know of in the universe, a black hole where gravity is so strong that not even light can escape, will eventually be destroyed by the movement of the vacuum around it. Nothingness is literally corroding and consuming the most extreme something that exists. It is a poetic inversion of our intuitions about the relationship between existence and emptiness. Let's now address a question that may be brewing in your mind. If the vacuum is so teeming with activity, why don't we notice it directly in our everyday lives? Why does space seem empty when we look through it? The answer has to do with scales. Quantum vacuum fluctuations happen on extremely small length and time scales, much smaller than atoms, much smaller than anything our senses, or even our most sensitive instruments, can detect directly without carefully designed experiments. It's like asking why we don't see individual atoms when we look at a table. It's not because they aren't there, but because our eyes have limited resolution and the atoms are very small. Similarly, vacuum fluctuations are real and have measurable effects, but only when we do specific experiments designed to detect them, like the Casimir effect, or when we look at phenomena where they accumulate, like in Hawking radiation or contributions to particle properties. For size and time scales that matter in our daily lives, the vacuum behaves on average as if it were empty, in the same way that the surface of a lake appears smooth when viewed from afar, even though it is full of microscopic ripples. Furthermore, our bodies and brains are classical, not quantum systems. We are made of trillions of atoms whose collective behavior is well described by classical physics. The quantum effects of vacuum fluctuations cancel out or become insignificant when you have such large numbers of interacting particles. This is the essence of what physicists call decoherence. Large systems quickly lose their quantum properties due to interaction with the environment. But that doesn't mean the effects aren't there. Every atom in your body is constantly interacting with the sea of virtual quantum vacuum particles around it. These interactions slightly change the energy levels of electrons in atoms, and these tiny changes, called Lamb shifts, have been measured with incredible precision and agree perfectly with theoretical predictions. So yes, the movement of the vacuum is affecting you now. It is affecting every atom in your body, but in such subtle ways that you would never notice without sophisticated scientific equipment. It's like asking if you feel the neutrinos passing through your body. Trillions of them are passing through you right now from the sun, but they interact so weakly with matter that you would never know. The universe is full of phenomena that are real but invisible to our unaugmented senses. Now, let's explore one of the most speculative but fascinating ideas about vacuum motion. The possibility that our universe is just one bubble in a multiverse of infinite bubbles from different vacuums, each with its own laws of physics. This is the idea of the vacuum landscape in string theory. String theory, which attempts to unify quantum mechanics and gravity by postulating that fundamental particles are actually tiny vibrating strings in extra dimensions of space, predicts an astronomical number of possible vacuum states, perhaps 10 to the 500th power or so, each corresponding to a different way of extra dimensions if curl up. Each of these vacuums would have different values for fundamental constants, such as the electron charge, the force of gravity, and the masses of the particles. Most of these voids would not allow the formation of complex structures like atoms or life, but a few would. The idea of eternal inflation combines this with cosmic inflation. In an eternal inflationary universe, inflation never completely stops everywhere at the same time, but continues in some regions while ending in others, creating bubbles like ours where inflation ended and matter and energy were created. Different bubbles can decay to different voids in the string theory landscape, so each bubble would essentially be a separate universe with its own laws of physics. Our universe would be just one bubble in an infinite cosmic foam of universes, all arising from the movement and decay of the inflationary vacuum. This is speculative, and we have no direct evidence for the multiverse, but it illustrates how deeply our understanding of the vacuum and its properties is connected to the most fundamental questions about the nature of reality and why the laws of physics are what they are. If these multiverse ideas are correct, then the motion of the vacuum is not only responsible for the structure within our universe, but for the existence of multiple universes with different physical realities. The vacuum would be the fundamental substrate of all possible existence, not just real existence. And if you're finding all of this absolutely mind-blowing, that these revelations about the fundamental nature of reality are expanding your mind in ways you didn't even imagine were possible, then, like this video, subscribe to the channel, and turn on notifications because we have so many more deep explorations into the mysteries of the cosmos waiting for you. And each video is a unique journey that will make you question everything you thought you knew about the universe. There is a deep philosophical question that arises from all of this. If the vacuum has properties, if it is in motion, if it contains energy and structure, then is it really empty? Or are we simply using the word vacuum confusingly to describe something that is actually a highly complex and dynamic state of the universe? Some physicists argue that we should abandon the idea of a vacuum as void altogether and recognize that what we call a vacuum is actually the ground state of a collection of quantum fields that permeate all of space. These fields are as real as matter. They are just not made of localized particles. The electromagnetic field, the electron field, the Higgs field, and all the other fields of particle physics exist everywhere in space-time. And what we call a vacuum is simply the state where these fields have their minimum energy and no excitation in particle form. But this minimal state is not nothing. It is a specific state with specific properties, and these properties determine everything about how the universe behaves. When you create a particle, you are not creating something out of nothing. You are exciting one of the quantum fields above its vacuum state. When the particle annihilates, it does not disappear into nothingness, it returns the field to the vacuum state. The distinction between something and nothing becomes blurred when you realize that they are both states of the same fundamental substrate of quantum fields. Neil deGrasse Tyson likes to emphasize that science often reveals that reality is far stranger and more wonderful than anything we could have imagined. And the nature of the vacuum is a perfect example of this. Who would have imagined that empty space would be so rich in structure and dynamics? Who would have predicted that nothingness would be something so fascinating and fundamental to the existence of the universe? Let me now connect all of these concepts in a way that I hope solidifies your understanding of the big picture. The quantum vacuum is not just a technical detail of particle physics, but rather a central player in virtually every aspect of physical reality as we know it. Quantum vacuum fluctuations explain why particles have the properties they do, through effects such as the Lamb shift and the electron's anomalous magnetic moment. Vacuum energy could be the dark energy that is accelerating the expansion of the universe and determining its ultimate fate. Vacuum fluctuations during cosmic inflation created the seeds of all large-scale structure in the universe. Vacuum fluctuations near black holes cause Hawking radiation and the eventual evaporation of black holes. The possible instability of the vacuum could, in principle, cause the end of everything we know. And speculatively, different vacuums in a multiverse could explain why the laws of physics are what they are. The vacuum is in motion in all these contexts, NNT, not in the sense of moving through space, but in the sense of being dynamically active, constantly doing something, constantly participating in the physics of the universe. It's a protagonist, not a background. And this fundamentally changes how we should think about the structure of reality. It's not that there are particles and forces happening on an empty stage of space and time. It's just that space and time themselves are made of quantum fields in various states, and all the phenomena we observe are patterns of excitation and movement in those fields. Vacuum is the ground state, but fundamental does not mean simple or inert. It means the starting point from which all the richness of physics emerges. It's like the keys on a piano. The unpressed keys are the fundamental state, but they are not nothing. They are the possibilities of all the songs that can be played. The void is like this. It is the silence from which the entire symphony of the cosmos emerges, but it is a silence that is already charged with all possibilities, vibrating with potential, waiting to manifest the full complexity of the universe. Have you ever stopped to think that the simple fact that you exist, that you are conscious, that you are processing these ideas now, is a direct consequence of the movement of the vacuum? The atoms in your body were forged into stars that only exist because vacuum fluctuations during inflation created the seeds of structure that eventually collapsed into galaxies and stars. Your galaxy is being swept away by the accelerated expansion of the universe caused by dark vacuum energy. The electrons that carry nerve signals in your brain have the properties they do because they are constantly interacting with the quantum vacuum's sea of virtual particles. There is nothing in your existence that is separate or independent of the vacuum and its properties. You are a transient excitation in the quantum fields of the universe, arising in the same way that virtual particles arise from vacuum fluctuations, except you persist for longer, for a few decades instead of a fraction of a second. But fundamentally, you and the vacuum are made of the same substrate. This realization can be humbling or liberating, depending on how you look at it. Humbling because it reveals that we are not as special or separate from the rest of the universe as we might like to think. Liberating because it means that we are an integral part of the cosmos, not external observers, but internal participants in its evolution and development. The universe is not a stage where life happens. Life is part of what the universe does, one of the ways in which the quantum fields of the vacuum can organize themselves into complex, self-aware structures. Neil deGrasse Tyson often comments on the astonishing fact that the atoms in our bodies were literally forged in the hearts of massive stars and scattered throughout the cosmos when those stars exploded in supernovae. We are, literally, stardust. But we can go even deeper. The quantum fields that make up these atoms are the same fields that exist throughout the universe, in the same vacuum ground states, and the particles that make up our atoms are simply local excitations of those fields. We are wave patterns in the quantum sea of the vacuum, and when we die, these excitations eventually decay back to the vacuum state, returning the borrowed energy to the cosmos. But information about the pattern we were can persist in other forms, in memories, in causal effects we have had in the world, and, according to some interpretations of quantum mechanics, in even more exotic forms that we have barely begun to understand. Which of these perspectives on our connection to the void resonates most with you? The fact that we are fundamentally part of the same quantum field structure that makes up the vacuum, or the idea that the vacuum's fluctuations created the conditions for our existence? Comment your reflection. I love seeing how these profound scientific ideas impact the way people think about their place in the universe. Now let me address some of the open questions and ongoing debates about the nature of the vacuum, because it's important to recognize that we don't have all the answers. The cosmological constant problem, the discrepancy of 120 orders of magnitude between the predicted and observed vacuum energy density, remains unsolved. Theoretical physicists have proposed several ideas. Perhaps there is a cancellation mechanism that we don't understand. Perhaps the high-energy physics that we can't test directly is very different from what we think. Perhaps dark energy is not vacuum energy, but something completely different like a dynamic quantum field called quintessence. We don't know. The question of vacuum stability is also open. Measurements of the Higgs boson's properties are continually improving, but uncertainties still allow our vacuum to be metastable or absolutely stable. More data from the Large Hadron Collider and future particle colliders may eventually resolve this. The unification of quantum mechanics and gravity, which is necessary to fully understand vacuum physics in extreme regimes like the Big Bang or the interior of black holes, remains elusive. String theory is one candidate, loop quantum gravity is another, but neither has been confirmed experimentally, and neither may be completely correct. The question of the multiverse and whether different voids actually exist in other causally disconnected regions of the cosmos is fundamentally difficult to test because, by definition, we cannot observe causally disconnected regions. Some physicists argue that untestable ideas are not real science, while others argue that if they emerge naturally from theories that make testable predictions in our observable universe, they are legitimate scientific speculations. These debates are healthy and are part of the normal process of science dealing with issues at the frontiers of knowledge. The lesson here is that although we know a lot about the properties and behavior of the quantum vacuum, there is still much we don't know, and intellectual honesty demands that we acknowledge these uncertainties. What makes science so powerful is not that it claims to have all the answers, but that it has rigorous methods for distinguishing between what we know well, what we know poorly, and what is pure speculation. The ideas I discuss in this video range along this spectrum. The Casimir effect and the Lamb shift are extremely well-established experimental facts. Dark energy is a well-confirmed observation, although its exact nature is debated. Cosmic inflation is a strong theory with growing evidence but not completely proven. And the vacuum multiverse is a theoretical speculation that may or may not be correct. These are all fascinating ideas that help us think about the nature of the vacuum, but it's important to keep in mind which ones are highly certain and which are more speculative. I want to close by reflecting on what all this means for our understanding of reality and our place in it. The discovery that the vacuum is not empty, but is teeming with quantum activity and energy, is one of the great revelations of 20th century physics, and its implications are still being explored in the 21st century. It forces us to recognize that reality is fundamentally much stranger than it seems, that our senses give us only a crude and misleading approximation of what is really happening at the deepest levels of nature. Vacuum motion is not just a technical curiosity, but a key to understanding the most fundamental questions: why the universe exists, where it came from, where it is going, why the laws of physics are what they are, and what it means to exist in a quantum world. Neil deGrasse Tyson has been a tireless advocate for sharing these complex ideas with the general public because he understands that they are too important to be left to experts alone. When you understand that the vacuum is in motion, that nothing is something, that the distinction between existence and non-existence is not as clear as it seems, you begin to see the universe with different eyes. Every cubic centimeter of space, even the seemingly empty intergalactic space between galaxies, is buzzing with quantum activity, participating in the cosmic expansion, carrying the dark energy that will determine the ultimate fate of everything. There is no place in the universe that is truly empty or inert. Even the void is doing something, it is changing, it is contributing to the great tapestry of physical reality. And that, to me, is simultaneously frightening and profoundly beautiful. Scary because it reveals how little our everyday intuition prepares us to understand the true nature of reality. Beautiful because the universe is incredibly richer and more fascinating than anything we could have invented with our limited imaginations. Reality surpasses fiction in strangeness and wonder. The moving vacuum is just one example of how science continues to surprise us, to expand our horizons, to show that there is always more to discover, always more depth to explore. We live in an extraordinary time where we have the mathematical and experimental tools to probe these profound questions about the nature of emptiness and existence, and where we can share these discoveries widely through channels like this, connecting millions of people around the world in a shared quest for understanding. And if you've felt your mind expand along this journey, if these revelations about the movement of emptiness have changed the way you think about space, about time, about the nature of reality, then please like, subscribe, go to the channel, turn on the notification bell, and share this video with someone you think would love to have their mind blown in the same way. Because it is through sharing knowledge and wonder that we collectively expand our understanding of the cosmos. And commenting on which part of this exploration impacted you the most also helps a lot, not just for the algorithm, but for me to know what type of content resonates most with you and what directions to explore in future videos. The universe is vast and full of mysteries, and we've barely begun to scratch the surface. The moving vacuum is just a gateway to even deeper questions about quantum space-time, emergent gravity, the nature of consciousness in a quantum world, and the ultimate destiny of everything that exists. There is so much more to explore, so much more to understand. And I hope you will continue this journey of discovery with us, because together we are participating in one of humanity's great intellectual adventures. The quest to understand the cosmos of which we are a part, even the most counterintuitive and disturbing aspects, like the hidden movement at the heart of the void itself.